Welcome to my video on verifying trig identities. I am a mathematics teacher, and verifying trig identities is going to be the topic of this video today. If you don't already have your identities right next to you, I suggest that you have them to refer back and forth to while we are proving some trig identities. So let's go ahead and talk about what does it mean to verify trig identities. When you're asked to, quote, verify an identity or prove an identity, you're being asked to show that one side of the equal sign equals the other side. And that's for all the variables. And you're going to do this by manipulating only one side. So you get to pick the side that you want to work on. Generally, we pick the side that is the most complicated because it is easier to take the complicated side and break it down to match the easier side than it is to take something that's very small, like for example, the problem I have in front of me, cosine squared of x. It's harder to take that term and build it up to match the other side. But in general speaking, you get to pick whatever side you want to work on. Now, I do want to point out that there are multiple ways that you can prove a trig identity. I'm going to show you one way, and this way is going to use the identities. It's going to use algebraic techniques to simplify and manipulate, and all of these techniques are sound. Now, if you're sitting there and you're like, well, I saw this instead, and can I use this? As long as the identities you are using are valid identities, as long as you are using sound algebraic techniques, then whatever method you choose to use is in fact valid. So let's go ahead and get started. So I have an identity right here in front of me, and we're going to prove that one side equals the other. As I mentioned, choose the most complicated side. So for us, the most complicated side is going to be the left-hand side. As you're working on these problems, it's really helpful to have your identities right next to you so that you can refer to those identities when you need them. As you practice more problems, it's going to be a lot easier for you to prove or verify your identities because you're going to have the trig identities memorized. Now, do you need to have the trig identities memorized? You pretty much do. We use these identities in not just Algebra 2, but PreCalculus and Calculus. They do pop up, and when you get to the calculus level, there is so much that is new to you that you're going to have to solve and find. The last thing you want to do is have to have all these aids next to you to refer to. You want to be able to get through that material a lot quicker and focus on the new concepts. So I suggest that you have the trig identities memorized, and it'll just make things a lot easier for you. All right, so I'm going to pick the left-hand side, and when you're looking at the trig identities, one of the things that pops up a lot are the Pythagorean identities. There are a few of them, and there are different versions of them. So the most common one that we use is sine squared plus cosine squared equals 1. But you can solve for cosine squared. You can solve for sine squared. And you are allowed to substitute in what those terms are equal to. So for example, if I am looking at sine squared of x plus cosine squared of x equals 1, and I solve for cosine squared of x, I get 1 minus sine squared of x. And that means wherever I see cosine squared of x, I can replace it with the expression 1 minus sine squared of x. You can do the same thing with sine squared of x by solving for that, and you get 1 minus cosine squared. Let's work on the left-hand side, And one of the Pythagorean identities is the one that I just went over with sine squared and cosine x, but there actually is one with cosecant squared of x. And with cosecant squared of x, this is the Pythagorean identity that is for cotangent squared. So cotangent squared of x is the same as cosecant squared of x minus 1. So I'm going to use substitution, and I'm going to substitute out that expression for its trig equivalent. I'm going to go ahead and just leave the denominator the same. And I'm not even going to touch the right-hand side. So again, going back to verifying trig identities, you are only focusing on one side of the equal sign. You're going to manipulate it and make it match the other side. That way you're proving that both sides do in fact equal each other. So I'm not even touching the side with cosine squared of x. You can leave it blank. You can draw like an X through there. You can draw a little squiggle, whatever it is that will help you not touch that side. Moving on to the next step. Notice how I have cotangent squared x, cosecant squared x, and I need it to match cosine squared of x. So what that means is I need to remove these trig functions, cotangent, cosecant, and I need to turn them into sines and cosines so that they simplify down to cosine squared of x. So what I'm going to do is I'm going to use the identities. Now, there's lots of identities, so the question is which one are you going to use? Well, you want things to simplify. So I need to turn this 1 over cosecant squared of x, yes, it's 1 over, because the way that you can also look at this is, I'm going to go ahead and write it off to the side, 1 over cosecant squared of x times cotangent squared of x. And these two expressions are exactly the same. So I'm going to turn 1 over cosecant squared of x into sine squared of x using the reciprocal identity. So this guy right here is sine squared of x. And I'm going to use a different color. Cotangent squared of x. Now I could turn this into 1 over tangent, but as I said earlier, we're trying to get things to simplify. So if you change everything into sines and cosines, then you're going to start to see things simplify. So cotangent squared of x using the quotient identity is cosine squared of x divided by sine squared of x. Again, leaving the right-hand side alone. Now when I go to simplify, I notice that I have sine squared on top, sine squared on bottom. They reduce to 1. Anything over itself is 1. And I'm left with cosine squared of x. This does in fact match the right-hand side. When we are working with mathematical proofs, which this is, I have pretty much a 2-column proof. And with this proof, I can show that I am done in various ways. It's up to you what you want to use. Sometimes teachers are very specific on how they want you to end your proof, but there are a variety of ways. The ones that I've learned from all of my professors is that I can box my closing line that shows that I have two sides that match each other, that they're equal to each other. I have seen teachers use a check mark. Normally in paragraph proofs, we use the next closing argument, which is QED. It's basically, I think, Latin for saying we're done. You can use QED. I usually see this one in paragraph proofs. And then the other one that I've had is a tiny little box. So I've seen a variety of ways to show that we're done. It's up to you, it's up to your professor. I'm gonna just go ahead and box them. That way it draws your attention to that closing argument, that closing line, saying that, hey, I got to this point, I'm proud of myself, and there you have it. Now, I don't want you to feel discouraged if you're not able to get these proofs done in 2 steps, 3 steps. The point is that you are using correct identities and you are using correct algebraic techniques. So if it takes you 10 steps to prove an identity and it takes somebody else only 5 steps, there's nothing wrong with that. You do what works for you and what you see. If you saw something else and you want to use that instead, there's nothing wrong with that. In fact, I want to go over another technique for verifying this specific identity that is completely valid. And it's actually a technique that we use quite often. And that technique is splitting up, and I'm still sticking to the same side. This technique is splitting up your one term into multiple terms. So we know from just basic algebra that if I have something like x plus 3 divided by 2, I can split this one term into 2 terms. Since the quantity x plus 3 is over 2, that means x is over 2 and 3 is over 2. You can kind of think of it as distributive property. So if I look at this as distributive property, my scalar is 1/2 and I'm multiplying it by x plus 3. Then when I go to distribute, I get x over 2 plus 3 over 2. So when you have one term in the denominator, you can go ahead and split up that term into multiple terms. But what you can't do is the reciprocal of that. If you have 2 divided by x plus 3, you cannot split them up. You can't split up a sum or a difference in the denominator. So if I were to look at this the same way using distributive property, I would have 1 over x plus 3 being multiplied by just 2. Well, that's the same thing as 2 over x plus 3. So notice that when I look at the reciprocal of x plus 3 divided by 2, they don't match. So I'm just going to caution you right there for all of the other identities that you prove. But since this particular problem has one term in the denominator, I can split this up. So I'm going to kind of do like a little mini proof. I'm going to split up this one term into 2 different terms. So I would get cosecant squared of x over cosecant squared of x minus 1 over cosecant squared of x. And again, that's going to equal cosine squared of x. You're probably wondering why I draw this line. It's to keep myself organized. If this is your first time verifying trig identities and you're not feeling very confident about the proofs, I suggest drawing that vertical line. It really helps keep yourself organized and focused. Going back to the left-hand side, anything over itself is 1. So this guy reduces to 1. So I end up getting 1 minus. This term, 1 over cosecant squared, is the same thing as sine squared of x using the reciprocal identity. Then this is a Pythagorean identity that we went over before. So we have cosine squared of x. Is it less work? Yeah. Did I use the same method as my previous method? No. But did I still get the same thing? Yes. So notice how they match. This is what I mean by there are multiple ways that you can prove trig identities. So don't get discouraged if you are checking answers with your textbook or with your teacher. As long as you used valid identities and valid algebraic techniques, you are golden. So this is an easy trig identity to prove. I have another one that's also kind of simple, but has the reciprocal of what we previously had. So notice with the previous problem, we had the difference in the numerator and the single term in the denominator. But on this one, now it's flipped. So this one's going to be possibly a little bit longer. But just because it's longer doesn't mean that it's a harder problem. It's just going to take maybe more time. One of the questions I get asked a lot is, what do you do when you get down to the very bottom and you need more space? Like, what do you do with your proof? Do you just like end it there? Like, where do you continue? Well, you usually just draw a little arrow, continue off to the side, and then draw another 2 column, because you have to keep your equal sign equal. You've got a left side, you've got a right side, and an equal sign in the middle. So if you get to the very end of your page and you need more space, just draw an arrow showing where the rest of your work is at, and then continue with another 2 columns to finish your proof. When I look at this problem, to me, I see the right side being the most complicated because of that fraction. So I'm going to work on that side. And when you have a problem like this one, where you have a sum or a difference in the denominator, and in that sum or difference, none of the terms are squared. So this is just cosine of beta. My suggestion is to use conjugates. So a conjugate is when your terms are the same, but the sign between your sum or difference is the opposite. So for example, if I have a plus b, the conjugate is a minus b, and vice versa. If I have a minus b, the conjugate is a plus b. So the conjugate of the denominator is 1 plus cosine of beta. And I'm going to multiply the bottom by 1 plus cosine of beta. And whatever you do to the bottom, you also do to the top, and vice versa. Okay, so let's talk about why we're using conjugates. So if you remember back from Algebra 1, difference of 2 squares. So difference of 2 squares is an expression and its conjugate. And when I multiply an expression and its conjugate using distributive property, what ends up happening is the middle 2 terms, they end up simplifying to 0. So I get my a squared, I get minus a times b plus a times b. So those 2 terms are going to reduce to 0. Then I get b times negative b, which is negative b squared. So this is difference of 2 squares. Now what's nice about this with the trig identities is the following. 1, it's going to create a squared term. So multiplying cosine of beta times cosine of beta is going to give me cosine squared. And what do we think of when we see the squareds? Ding, ding, ding. Can you answer that? We think of the Pythagorean identities. So conjugates are helpful because they will allow us to use the Pythagorean identities. So I'm going to go ahead and multiply using distributive property. But here in the numerator, I'm going to actually keep them as factors, as sine of beta and 1 plus cosine of beta. But in the denominator, I'm going to distribute. So 1 times 1 is 1 squared, which is 1. The middle 2 terms are going to cancel and become 0. So I get cosine of beta minus cosine beta is 0. And then negative cosine beta times positive cosine beta is negative cosine beta squared, or cosine squared beta. Now, why did I leave the numerator as factors? So this has 2 meanings behind it for me personally. One, I like to do one step at a time. If I'm trying to combine everything into one step, I'm going to get lost. And I'm going to forget what I did, how I did that. And then when I'm trying to look back on my work, I'm going to be like, well, I don't know what I did, and have to do the problem over again. So I prefer personally to write each step out. It doesn't matter to me if it takes an extra 10 seconds to write it out. I would just rather do that. It's going to save me stress and headaches later. The other reason that I like to leave the numerator, in this case the numerator, in the factored form is because maybe things will simplify. So maybe there's going to be a 1 cosine beta that I can just boop, boop, cross out. Maybe there's going to be a sine of beta that I can just boop, boop, cross out. So I'm going to leave the numerator in factored form because I'm hoping things will simplify, because that is what we're doing, right? We're simplifying. So I see the 1 minus cosine beta. We talked about this earlier. It's the Pythagorean identity. So I'm going to go ahead and replace that with sine squared beta and leave the numerator alone. And just as I said, woohoo, we are going to have a sign on top and a sign on the bottom that we can reduce. We are allowed to do this because of multiplication. So I can go ahead and reduce this sign with one of the signs in the denominator. I'm left with 1 plus cosine of beta over sine of beta. And at this point, you're probably thinking, wow, this looks nearly identical to what we started with. It's just they're flipped, and instead of the minus, we have a plus. Like, what the heck just happened? Well, this looks like the previous problem, right? Where we have a sum or a difference in the numerator and a single term in the denominator. And what can we do if we have one single term in the denominator? We can split them. So this actually really did help us. I can take the sine of beta and I can write it over all the terms in the numerator. So I'm going to go ahead and do that. And what I'm going to do now is refer back to the other side, the left-hand side, and I'm going to remind myself, hey, what am I trying to achieve here? What is my purpose of all of this work? Am I going in the right direction? So kind of take a step back and evaluate where you're at. I have a cosecant of beta plus a cosine of beta. And when I take a look at my work, I have 1 over sine of beta. Well, using the reciprocal identity, that's the same as cosecant, so perfect. And then cosine over sine, using the quotient identity, is cotangent of beta, so perfect. This is perfect. I get cosecant of beta plus cotangent of beta, and that's exactly what I was trying to achieve. I'm going to box to just show, hey, I'm done. I got to exactly where I needed to go, and I'm done. So let's just kind of review and remind ourselves what it is that we did. So we choose the most complicated side. It's easier to break that down. When you have a sum or a difference in the denominator, try to use conjugates to get it out of the denominator. Whenever you see squareds for your trig functions, think of Pythagorean identities. Try to split up your terms if you have a single term in the denominator. Remind yourself every now and then what it is that you're trying to achieve. So look at the other side. Where is it that you're supposed to be going? What's nice about these problems is that the answer is already given to you. This is my answer for this problem. It's over on the left-hand side. I am trying to achieve this. So as long as I am using correct trig identities and correct algebraic techniques, and I have the answer in front of me, I can prove this identity. These are easy trig identities to prove or verify, and I hope this video was really helpful for you. In the comments below, let me know if there are other types of problems that you are interested in me solving, or if you have any questions. And don't forget to like and subscribe so that you can get more homework help in the future as I post new videos.